We have been working on the GIESEPP MP project with all the consortium members, and they have prepared some interesting facts about our project and its implementation, as well as some questions. Watch the video and see if you can answer those questions.
Within GIESEPP MP, a group of specialists is developing the first gridded ion engine standardized electric propulsion system. Each partner is responsible for a different technology within the consortium. MP stands for medium power range, which is typically the geostationary satellites. For electric propulsion, one usually uses less propellant, as the electric propulsion system has a much higher specific impulse compared to chemical propulsion systems. For all-electric geostationary satellites, you usually have two different operational modes. One is the station-keeping mode with a high specific impulse and a lower thrust, and one is the orbit-raising mode with a higher thrust to minimize transfer times to the orbit. By using electric propulsion, you have the chance to use more payload on board the satellite, as you're more mass efficient than chemical propulsion. And this will, of course, reduce costs for the whole system.
So the Justus Liebig University of Gießen in Germany is responsible in the project for providing scientific support, which helps the other partners to improve their ability to optimize or to develop this electric propulsion platform, which is the goal in the project. So in Gießen we have a long heritage in developing ion thrusters, especially the radio frequency ion thruster that is part of the project was developed in the 1960s in Gießen by a professor called Horst Löb, who is a very famous person in EP. And we have really one of the first test facilities at that time in the 1970s, one of the biggest test facilities in Europe. And we are developing diagnostics and thrusters for almost 60 years up to now. So we focus in the project on a diagnostic of the so-called plume. This is the exhaust of the ion thruster. And we are looking for ion beam distributions, that we want to know how many ions come out of this ion thruster and what energy do these ions have. This is important to calculate the thrust that a thruster provides in the end, and also the energy gives us information about a potential damaging of surfaces on a satellite which may be hit by the ion plume, by the exhaust plume. We will conduct these experiments in a special vacuum facility, and the facility itself has to provide or simulate a space condition, which means we have to create a very good vacuum, and we do that with special cryogenic vacuum pumps which have a pumping speed of about 150,000 liters per second. The facility itself has a size of 2.5 meters in diameter and a length of 6 meters, and we need this big facility to let these really big thrusters operate, and the ion beam itself doesn't or shouldn't collide with the walls of the chamber. And that's why we need such a big vacuum facility for an ion thruster.
We at JLU are not only conducting experiments, we're also simulating the thruster. We do that because we think it's a fitting complement to better understand the physics behind the thruster. And what we want to do is to calculate the grid erosion of the thruster to estimate the lifetime of the system.
We in Airbus GIESEPP are responsible for developing the PPU for the electric propulsion system. The power processing unit, or the PPU, is the unit responsible for controlling and powering all the other elements of the electric propulsion system. The PPU has therefore to control all the currents and voltages that are supplied on the neutralizer or thruster units, and also has to regulate the fuel going through the valves of the fluidic system. To do that, the PPU is composed of several power sources that are capable of adjusting dynamically the power they deliver, and they can do so reacting to a command from the onboard computer, or they can do so in a fully automatic way. leading the system from a standby point to a full thrust mode of operation. As the PPU is the brain of the electric propulsion system, it's also responsible for protecting it against unexpected events or failures. One typical case is the beam out events that are common in the gridded ion thrusters. In those cases, the PPU has not only to protect itself, but it also has to be able to automatically recover in the shortest amount of time. One of the main challenges that we are facing in GIESEPP MP is to respond to real market needs. That is constantly asking for cheaper products with better performances and lower mass and volume figures. To do that, Airbus GIESEPP is introducing the latest technology in power electronics in designs that carry decades of expertise.
The result is a PPU based on GOTS, gallium nitride transistors and digital control, which has reduced dimension and mass and can achieve high efficiencies and provide a wide configuration capability, including in-flight adjustment of the operational points. All these performances make the PPU a very attractive unit. But in order to drive its cost down and achieve a real competitive product, the manufacturing process has to be industrialized. The use of GOTS is a very important step, but it has to be combined with automatic manufacturing and testing processes. Airbus GIESEPP is also using a modular approach in the PPU design, following the trend of the previous GIESEPP phase. This modular approach will help our teams with the manufacturing, testing and assembling of the unit, as well as opening the possibility to escalate the design to a higher power needs.